cryptography feasible under P equals NP.
So yeah, this is going to be pretty informal. Thanks, Robert, for also using the board and not making me feel like I'm the only one who didn't prepare slides and everything. So yeah, I'm interested in the foundations of cryptography more generally, but today I guess I'll briefly talk about a theme, I guess, in some of my work, which is trying to understand what you can do as a cryptographer if, let me find a marker, if P equals NP. Like, can we do crypto if P equals NP? So, right, the answer is sort of no under classical definitions, right? One-way functions don't exist. In some sense, one-way functions, or in some very rigorous sense, one-way functions are minimal for all of cryptography. But maybe there's something interesting that can be done even if P equals NP. So today, I'm just going to talk about two specific sort of lines of work, which at least seem to be independent of P versus NP. You can hope to get some sort of security guarantees. So one is easy to define and motivate, and easy to describe the results because basically we don't know anything about it. But I'll start with that because it's easy, and then I'll talk about something that's more complex and difficult to define and motivate, but we understand a lot better. Okay, so the first topic that I want to speak about is fine-grained cryptography. So what is sort of the object that we care about the most here? Or maybe not the most, but something that we're interested in. So, right, you're all familiar, I assume, at least those from the MCSP, the meta complexity program, are familiar with the notion of a one-way function. So, right, the one-way function, it's easy to give an input x. It's easy to compute f of x, but it's hard to invert f, right? It's hard to recover x from f of x. Okay. So what is so right? This is a one-way function, and it's a one-way function, right? What is a fine-grained one-way function? Well, it's exactly the same, except we're going to be more careful about what we mean by easy and hard. So easy here will mean, say, for example, it's computable in essentially linear time. It's easy to compute f of x, very easy to compute f of x. And hard, as opposed to most traditional cryptography, hard means hard for any probabilistic polynomial time adversary. Hard here, we just want to say, okay, like, is it hard for anyone running in, say, quadratic time? Okay. So as far as we know, right, it could be that P equals NP, but your fastest SAT solver runs in n to the 1,000 time. And then there's no obvious contradictions here. It's totally possible that such an object could still exist. And the hope is that because it's independent of P versus NP, and this is sort of why we started looking at this, that maybe you can prove more interesting things. The sad story is that we haven't been able to sort of prove right? Any one-way function is inherently a fine-grained one-way function because it's just even harder. Well, I guess if it's very easy to compute, but you can do sort of complexity leveraging to make it easy to compute. And it will be extremely hard. But we were hoping to get sort of more natural candidates. But still, it's been, I guess, 6 years now or something like this, and we're still not here. There's sort of natural problems that you can conjecture are fine-grained one-way functions, but sort of how these conjectures aren't very interesting. You can take a problem like planted cake leak or something, and you can say, like, right? This basically is a one-way function or planted k-sum. I'm not going to define these problems, but there are these natural sort of problems, algorithmic problems that very naturally lead to these objects, but somehow it's not, there's no theory there that's particularly interesting. There's other notions of fine-grained cryptography, however, and here the connections get more interesting. But yeah, I'd be very interested, perhaps this semester. Maybe there's we can come up with sort of a more general treatment of these kinds of objects, right? I mean, I don't see exactly how you would connect it to Kolmogorov complexity, given that there's like this tight, fine-grained aspect, but I'd be happy to explore this. Okay, so this is the first one, easy to define and describe because there's really not a lot to say. The second object I'd like to introduce is something called a non-malleable code. So this is something that came out of tamper resilience in cryptography. Maybe the motivations are slightly less clear. I'm not going to talk about so much about the original motivations for this object, but I'll try to. Instead, I think it's a very interesting object. I try to at least describe to you what it is. So in a traditional sort of coding setting, right, you want to send a message through a channel, right? In error correcting codes, you want to recover, right? You're going to encode your message and you want to decode it. In error correction, you want to recover the original message, right? Error correction becomes impossible if the channel can change all of the bits, right? So if we encode this as a code word, right? If the channel can just delete the code word and write some new code word to C prime, you'll get out some Y prime. And there's some Y that's not necessarily X, and there's really no hope of doing any error correction. So what is a non-malleable code? What you should think of it, a non-malleable code as the guarantee, we give up on recovering the message that you originally sent. And instead, we have this guarantee that basically this kind of attack where you just completely delete what happened before is the only thing that the channel can do on the entire experiment. So let me describe this a little bit more in depth. So in particular, right, so we have a non-malleable code. You have some channel, let's call it F, which is going to be in some class capital F, adversarially chosen. You're going to perform this experiment to get out some X hat or something. What we want informally the guarantee to be here is that either X hat is exactly the same as what you started with, or it's independent of X. I should mention that in this setting, it's inherent that you have randomness. These are randomized procedures. Okay, independent of X, and I also write. Additionally, we want that which case you're in is also independent of X. Right? You shouldn't be like tampering to bot. Right? And this is supposed to capture a notion of tamper resilience. Right? In particular, suppose X is like a number, like 10. Right? You shouldn't. We want tamper resilience. We don't want you to be able to produce a related encoding. So, right, you shouldn't be able to add 1. Given 10, I get 11. Given 13, get 14. Right? This came out of some attacks on signature schemes in cryptography. There's certain algebraic attacks where they were able to extract keys, but that's not super important. So you want tamper resilience, and right, this notion, right, either you get back exactly what was there, right? You get the key that you have in your crypto system doesn't change if X is a key, or it's just like completely random garbage that has nothing to do with what you started with. Okay? So this is sort of the informal definition of a non-malleable code. One way that you can formalize this that I think is compelling is you can say, right, that for all F, any function in this class of sort of channels that you want to build your non-malleable code against, this whole experiment should be close to some distribution. It can depend on this function. So there exists some GF, a distribution over the identity function and any constant function. So right, you have some distribution GF such that this whole experiment where I encode, tamper, decode is close to some distribution that's either just, right, I just randomly sample, I flip some coins and I either sample the identity function or I sample, right, a constant function. The constant function is, right, you should think of it as this experiment, right, with this example where you just delete what's on a channel and put something at your favorite code word in its place. Okay, why is this interesting? I think from a complexity standpoint is because, right, what we're trying to do here is we're trying to take some channel F, which you might think of as very inherently complex. Maybe, right, this is a poly-sized circuit or something like this, an n-squared sized circuit. You don't know what it is, but some arbitrary n-squared circuit. And we're transforming it into something by wrapping it and encoding and decoding into something that's incredibly simple, right? It either does nothing, it's the identity function, or deletes it and replaces it with a constant. And I think there's like an obvious parallel. I don't know, I'm almost out of time, but I'd like to sort of set up a parallel. There's a parallel here to, for example, like I think it's helpful to think about, say, for example, this Hastad switching lemma in this context. So, right, Hastad switching lemma says that if I take an AC0 circuit and I compose it with a random restriction, then the result is much, much simpler than this AC0 circuit, right? It's just this low depth decision tree. Right? I can collapse it to a decision tree. And with the non-malleable code, you have a similar sort of collapse. So we have a number of results that sort of make some sort of connection between circuit lower bounds and non-malleable codes and tamper resilience more explicit. So in particular, using techniques from certain circuit lower bounds, for example, we can show unconditionally that there exist codes where F is AC0 circuit, or right, a local circuit, which I guess is a subclass. Or for example, so if you're willing to assume strong circuit lower bounds, de-randomization style assumptions, we can show that you can build these objects even for like poly-sized circuits. And circuit lower bounds are inherent here, right? This decoding function is a hard to compute function. It's actually, so an explicit non-malleable code gives you explicit circuit lower bounds. The decode is hard to compute for the function class, and it's on average case hardness results, right? The encoding function will give you an explicit distribution that is hard to compute DO. Anyways, that's what I have to say.
Any questions before we move to the last one?
Yeah.
Complexity lower bounds, you need to do this for like P poly. They hold if P equals NP that they hold, or
they say basically that explicitly what it is E is hard for exponential size non-deterministic circuits.
Oh, okay.
So in some sense, it's saying that non-determinism doesn't help too much. Instead of saying, right.
And can you also build these objects from like the standard type of crypto library of assumptions, or is it only?
No, actually, that's a great question. So we have other work that uses crypto assumptions to build, where this, so here for this, like, right, the circular bound result, this is a statistical closeness. In the, right, if you use crypto, it's sort of, you're almost inherently getting computational closeness. It's hard for efficient distinguishers to tell which world you're living in. And even then, though, these aren't completely, we don't know how to do it from standard objects. They tend to be, all of our constructions that we know involve things that we don't know how to explicitly instantiate. So it's sort of uniform hash functions that we don't know how to build from standard assumptions. We know like a random oracle is good, but in some sense, this doesn't give you an explicit code, which is somewhat problematic.
Can maybe take the question offline? Okay. Okay, let's move on to the final talk of the Make the Fellow